Okay, so multiple linear regression model. The two variable model studied extensively in the previous unit is often inadequate in practice because in case of two variable model, for example x and y, like consumption and income, we have implicitly assumed that only income affects consumption. মানে আমরা ধরে নিয়েছিলাম যে কনজাম্পশন ইনকাম মডেলে শুধুমাত্র ইনকামের দ্বারাই কনজাম্পশন এফেক্টেড হয়. However, there can be other factors as well which can affect our consumption. But economic theory is often not so simple. Besides income, a number of other variables are likely to affect consumption expenditure, like the wealth of the consumer. As another example, the demand for a commodity is likely to be dependent not only on its own price but also on the prices of other competing or complementary goods, income of the consumer, social status, etc. This means that আমরা যে ধরে নিয়েছি বা we assume that uh, due to law of demand there is an inverse relationship between price and quantity demand, right? But this is very simple economic theory. There can be other factors as well which we assume to be constant can affect our quantity demand. Therefore, we need to extend our simple two variable linear regression model to cover models involving more than two variables. That's why we try to understand the multiple linear regression model. Adding more variables lead us to the discussion of multiple regression model, that is model in which the dependent variable or the regressand y dependent on two or more explanatory variables or regressors. That means in the previous simple linear regression model, we have assumed that y is only affected by x. In this model, in this multiple linear regression model, we will consider that while y will be affected by more than two x's. That means it can be affected by x1, x2 and other factors. The simplest possible multiple linear model is three variable regression with one dependent variable and two explanatory variable. Simplest version কি হতে পারে যে একটা y দুটো x affected করছে. হ্যাঁ. Throughout, we are concerned with multiple linear regression models, that is models linear in the parameter. They may or may not be linear in variables. এটা খুব ইন্টারেস্টিং একটা ব্যাপার যে আমরা ধরে নিই যে মডেলটা সবসময় লিনিয়ার ইন প্যারামিটারস হবে, ইট ক্যান মে নট লিনিয়ার ইন ভেরিয়েবলস. মানে আমাদের যে রিগ্রেশন ইকুয়েশনস গুলো হয় y equals to beta 1 plus beta 2x, beta 1 plus beta 2 x1 plus beta 2 x2 এরকম করে এখানে x can be x square, x cube, log x, it can be anything, but beta 1 beta 2 this must be linear, it should not be quadratic or cubic functions, right? So first of all we are assuming that the probability regression function PRF যেটা হয় সেটা equation 1 দিয়ে ডিনোট করছে yi equals to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui, where I denotes the observations, x2 and x3 are the variables, ui is the error term, and yi depends on x2 and x3. That means beta 2, beta 1, beta 3 are the parameters. Where y is the dependent variable, x2 and x3 the explanatory variables or regressors, u is the stochastic disturbance term, and I is the ith observation. Obviously in equation 1 beta 1 টা obviously intercept parameter. Basically intercept parameter কি দেখায় না, it gives the mean or average effect on y of all the variables excluded from the model. x1 x2 এগুলোর বাদ দিয়ে y এর উপরে mean effect. Although its mechanical interpretation is the average value of y when x2 x3 are set equal to 0. The coefficient beta 2 and beta 3 in simple linear regression model where we have only beta 2, we consider beta 2 as to be the regression coefficient. Whereas in case of multiple linear regression model, we cannot say that they are totally regression coefficients, rather partial regression coefficients. Just like partial derivative, we will when we consider beta 2, we will consider x3 to be 0, and when we will consider beta 3, we will consider x2 to be 0. When we will consider beta 2, x3 will be 0. When beta 3, x2 will be 0. That's why these beta 2 and beta 3 are known as partial regression coefficients. We continue to operate within the framework of classical linear regression model introduced in the previous unit, basically those Gauss-Markov assumptions. Specifically, we will assume that there is zero mean of Uy. That means expectation of Uy given the non-stochastic values x2 and x3 will be zero. That means expectation of the error term is zero. Next, we have assumed that there is no serial correlation. That means there is no autocorrelation, or you can say there should not be any correlation between the error terms of I and j observation. We are assuming this to get the multiple linear regression model in a more simplistic way. However, we will try to reduce these assumptions. We will try to relax these assumptions in the future classes. So first of all, we are assuming that there is no serial correlation or there is no autocorrelation between the error terms in the ith and jth observation. The third condition is that they are homoscedastic. Homoscedastic means that the error terms have common variance. For different error terms, we do not have different variances. Variance of Uy is equals to common variance sigma square. Next, fourth assumption is that we are assuming that Uy and x is obviously non-correlated, because in our regression equation we have yi equals to beta 1 plus beta 2 x, beta 1 plus beta 2 x2i plus beta 3 x3i plus uy, where obviously beta 1 plus beta 2 x2i plus beta 3 x3i is non-stochastic variable because we have certain fixed values of x2. Conditionally on those x2s we are getting some values. However, ui is the error term. If ui and x3i or x2i are getting correlated, that means that we cannot calculate beta 2 and beta 3 most efficiently. We cannot calculate partial regression coefficients if the error terms are directly correlated with x values, directly or indirectly. That's why we have assumed that there is no covariance or there is no correlation between the error term and the x variables. Okay. We have also assumed that no specification bias, that means the model is correctly specified, and we are also assuming that there is no multicollinearity, that means there is no linear relationship between x2 and x3, no exact collinearity between the x variables, or no exact linear relationship between x2 and x3. All these assumptions will get relaxed in the future classes, in the future units. When we will relax assumptions of no serial correlation, then we will try to understand the case of autocorrelation. When we will relax the assumption of homoscedasticity, we will try to understand the other part, that is heteroscedasticity. Similarly, if there is specification bias or if there is any kind of multicollinearity, we will again study in the later units. In addition, we also assume that the multiple linear regression model is linear in parameter. That means they are not non-linear in parameters. That the value of the regressors are fixed in repeated sample and that there is sufficient variability in the values of the regression. Obviously, these assumptions are similar to the simple linear regression model one. Assumption 6, that there is no exact linear relationship between x2 and x3, technically known as the assumptions of no collinearity or no multicollinearity, is new and needs some explanation. এটার মানে কি, এতক্ষণ কিন্তু x2 আর x3 যেহেতু ছিল না, শুধুমাত্র x একটা ভেরিয়েবল ছিল, তো কোনো মাল্টিকোলিনিটি ব্যাপার ছিল না in the simple linear regression model. However, when we will study the x2 and x3, that can be a multicollinearity problem. That means if we regress like consumption or income and wealth, that means consumption is the y variable and income and so let's say wealth is x variables, there can be a correlation between income and wealth. So if there is a correlation between the income and wealth, then we cannot calculate the partial regression coefficients. We cannot see the partial effects of income on consumption. We cannot see the partial effect of wealth on consumption, right? So there should not be any collinearity between x2 and x3. Assumption 6, that there is no exact linear relationship between x2 and x3, technically known as the assumptions of no collinearity or no multicollinearity, is new and needs some explanation. Informally, no collinearity means none of the regressors can be written as exact linear combination of the remaining regressors in the model. Formally, no collinearity means that there exists no set of numbers like lambda 2 and lambda 3, not both 0, such that this condition will occur. If such an exact linear relationship exists, then x2 and x3 are said to be collinear or linearly dependent. যদি এই ইকুয়েশনটা হোল্ড করে তাহলেই আমরা বলি জিনিসটা linearly dependent আছে. On the other hand, if the previous equation holds true only when lambda 2 equals to lambda 2 equals to lambda 3 equals to 0, then x2 and x3 are said to be linearly independent. তাহলে কোনো ইকুয়েশনই থাকবে না. Let's say, for example, if x21 equals to minus 5 times x3i, that means x2i is minus of 5 times x3i. তার মানে যত x3i বাড়ে অত x2i minus 5 করে কমে, basically 5 করে কমে. The two variables are obviously linearly dependent, and if both are included in the regression model, will have a perfect collinearity or an exact linear relationship between the two regressors. যদি আমরা x2 আর x3 দুটোকেই পুট করে দিই রিগ্রেশন ইকুয়েশনে, তাহলে আমরা obviously exact linear relationship পাবো. তার কোনো মানে হয় না, তার মানে আমি একটা ভেরিয়েবল নিলেই কাজ করলেই হয়ে যায়. For example, suppose that in equation 1, y, x2 and x3 represent consumption expenditure, income and wealth of the consumer respectively. In postulating that consumption expenditure is linearly related to income and wealth, economic theory presumes that wealth and income may have some independent influence on consumption. That means wealth is independently affecting our consumption and income is obviously independently affecting our income. That's why the theory presumes that wealth and income may have some independent influence on consumption. If not, then there is no sense in including both income and wealth variables in the model. If there is a correlation between income and wealth, let's say wealth equals to income square, then there is no required of adding both the variables in the model. In the extreme, if there is an exact linear relationship between income and wealth, let's say income equals to 5 times wealth equals to 5 times income, then it is not required to use both the variable in the model. We have only one independent variable and not two, and there is no way to assess the separate influence on income and wealth on consumption. To see this clearly, let's assume that x3i equals to 2 times x2i in the consumption income wealth regression. Then the regression equations টা কি হবে? Just x3i জায়গায় 2 times x2i বসিয়ে দেব. তার মানে এখান থেকে আমি যদি beta 2 আর 2 beta 3 কমন নিই, basically x2i পাচ্ছি plus ui. That means that beta 1 equals to alpha x2i plus ui, where alpha is nothing but beta plus 2 times beta 3. That is, in fact, we have a 2 variable and not a 3 variable regression. তাহলে মেইন প্রবলেমটা যেটা হয় সেটা হচ্ছে যদি x2 আর x3 লিনিয়ারলি রিলেটেড থাকে, তাহলে অ্যাকচুয়ালি আমরা দুটো ভেরিয়েবল পার্শিয়াল কোএফিসিয়েন্টস বের করছি না, বেসিক্যালি একটারই ভেরিয়েবল বের করছি. তখন সেটা 3 ভেরিয়েবল রিগ্রেশন মডেল দাঁড়ালো না, সেটা 2 ভেরিয়েবলই হয়ে যাবে. Moreover, if we run the previous regression model and obtain alpha, we cannot obtain beta 2 and beta 3. Why? Because this is one equation with two unknowns, beta 2 and beta 3. And we know that to get two unknowns, we need two simultaneous equations, right? To get the value of beta 2 and beta 3. And since by knowing alpha, we cannot determine the value of beta 2 and beta 3 because this is only one equation. So there can be infinite solutions, right? For example, x plus y equals to 5. There can be infinite values of x and y for which this equation holds. If we do not have simultaneous other equation in the form of x and y, we cannot get the value of x and y explicitly. Moreover, if we run the previous regression model and obtain alpha, there is no way to estimate the separate influence of x2 and x3 on y. For alpha gives the combined influence of x2 and x3 on y. Mathematically speaking, basically আমাদের কি দাঁড়াচ্ছে, alpha equals to beta 2 plus beta 3 is one equation in two unknowns, and there is no unique way of estimating beta 2 and beta 3 from the estimated alpha. In short, the assumptions of multi-collinearity requires that in the PRF we include only those variables that are not exact linear function of one or more variable in the model. Now we will try to interpret the multiple linear regression models. So given the assumptions of classical linear regression model, it follows that on taking the conditional expectation of y on both sides of the equation 1, we obtain basically আমরা যদি conditional expectation নিই তাহলে obviously error termটা থাকবে না. That means expectation of y given the values of x2 and x3, these are the conditional values, we are getting beta 1 plus beta 2 x3y plus beta 3 x3i. In other words, equation 2 gives the conditional mean or the expected value of y conditional upon the given or fixed values of x2 and x3. That means that for the given values of x2 and x3, we can easily get the expected value of y or the conditional mean value of y. Right? Therefore, as in the two variable case, multiple regression analysis is regression analysis conditional upon the fixed values of the regression, similar to the simple linear regression model. In that simple linear regression model, when we are writing the simple sample regression function, we are writing expectation of y given x, which is nothing but beta 1 plus beta 2 x. However, in the three variable regression model, there are one more term. That's why we are writing expectation of y given that x2y comma x3i is nothing but equals to beta 1 plus beta 2 x2y plus beta 3 x3i. This means that from equation 2, what we are getting is the conditional mean or expected value of y given the fixed values of x2 and x3. Now, what is the meaning of partial regression coefficients? Beta 2, beta 3 basically কি দেখায়? Obviously, these two are slope coefficients, but beta 2 and beta 3 basically কি দেখায়? If we differentiation আমরা পড়ে এসেছিলাম যে dy by dx যেটা আমরা করতাম সেটা সিম্পল একটা ফাংশনাল ফর্মে, বাট যখন দুটো ভ্যালু থাকতো, দুটো x থাকতো, মানে x1 x2 থাকতো, তখন আমরা পার্শিয়াল ডেরিভেটিভ করতাম. পার্শিয়াল ডেরিভেটিভ বেসিক্যালি মানে কি দেখাতো যে rate of change of y with respect to x1 for a fixed x2, right? This is nothing but beta 1, sorry, beta 2. So as mentioned, similarly beta 3 এর কি দেখাবে না rate of change of y with respect to change in x3 keeping x2 constant, holding x2 constant. So as mentioned earlier, the regression coefficients beta 2 and beta 3 are known as partial regression or partial slope coefficients. The meaning of the partial coefficients is as follows. Beta 2 measures the change in the mean value of y, that is expectation of y, per unit change in x2 holding the value of x3 constant. That means beta 2 কি দেখায় না in an average y কত চেঞ্জ করতে পারে due to 1 unit change in x2 keeping x3 constant. বোঝা গেছে? That's why যেহেতু আমরা x3 টাকে constant ধরে নিচ্ছি, just like we have understood about partial derivatives, this is also a kind of partial regression coefficients. Similarly, beta 3 measures the change in the mean value of y per unit change in x3 holding the value of x2 constant. This is the basic idea of partial regression coefficients, beta 2 and beta 3. So beta 2 shows the rate of change of mean value of y, that means in an average y how much y is changing due to 1 unit change in x2 keeping the value of x3 constant. Similarly, beta 3 shows the rate of change of y or the rate of change of mean value of y per unit change in x3 holding the value of x2 constant. Now we need to understand how we can derive the partial regression coefficients. Okay? Next, we will again use the OLS ordinary least square estimators to obtain the value of the partial regression coefficients. Similar to the previous unit, like previous lecture 1, we are again assuming that the PRF looks like this: yi equals to beta 1 plus beta 2 x2y plus beta 3 x3i plus uy. If we assume there are n number of variables, then we can obviously use mathematical equations in a matrix form and we can easily get the values of beta 1 and beta 2. Okay. For the timing, we are excluding from that mathematical part, just we are understanding the ideas. So yi equals to beta 1 plus beta 2 x2y plus beta 3 x3i plus uy, where y is the dependent variable x2 and x3 the explanatory variables or regressors, u is the stochastic disturbance term, and I is the ith observation. To find the OLS, obviously we need to understand we need to write the sample regression function corresponding to the PRF, which is yi equals to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i plus ui hat. This is for sample regression function, where obviously ui hat, just like the previous model, is the residual term, which is basically the sample counterpart of the stochastic disturbance term ui. So ui shows the population, the error term in the population function, and ui hat shows the error term in the sample function, sample form. Okay. Uh, as noted in the previous unit, the OLS procedure consisting of choosing the values of unknown parameters so that the residual sum of square RSS is as small as possible. আমরা যেটা আমরা আগেও করে এসেছিলাম যে অর্ডিনারি লিস্ট স্কয়ার কি করে না এই রেসিডুয়াল সাম অফ স্কয়ারটাকে যতটা মিনিমাইজ করা যেতে পারে। why sum of square? Because if we just use summation of ui hat, জাস্ট যদি আমি মিনিমাইজ করতে চাই রেসিডুয়ালটাকে, শুধুমাত্র সাম অফ রেসিডুয়ালটাকে, সেটা পসিবল নয়। why? Because summation ui hat can be 0 because some negative effects, some negative values and some positive values can cancel out, and that can lead to 0 summation ui hat. That's why we often use summation ui hat square, and we try to minimize this. So to minimize summation ui hat square, that means equals to summation of, if we write equation 2, equation 2 তে তুমি ভালো করে দেখো যে আমি যদি এই টার্মগুলোকে এইদিকে নিয়ে আসি তাহলে আমি সামেশন ui hat পাচ্ছি, আর তার হোল স্কয়ার মানে পুরোটার হোল স্কয়ার করা, তাহলে আমি থার্ড ইকুয়েশন পাবো। এবার ডিফারেন্সিয়েটিং দিস ইকুয়েশন পার্শিয়ালি উইথ রেসপেক্ট টু থ্রি আননোনস এন্ড সেটিং দ্য রেজাল্ট ইকুয়েশন টু 0, উই অবটেন, আমরা যদি ডেল সামেশন ui hat স্কয়ার বাই ডেল বিটা 1 hat করি, তার মানে বেসিক্যালি আমরা এই ইকুয়েশনটাকে রিগ্রেস করছি, রাইট? এই ইকুয়েশনটাকে রিগ্রেস করছি, ডিফারেন্সিয়েট করছি। তাহলে 2 টা আগে বাইরে চলে আসবে, 2 সামেশন yi মাইনাস বিটা 1 hat মাইনাস বিটা 2 x2i মাইনাস বিটা 3 x3i, বিটা 3 at x3i। যেহেতু বিটা 1 hat এর রেসপেক্টে ডিফারেন্সিয়েট করছি, তার মানে বিটা 1 hat এর আগে একটা মাইনাস আছে, দ্যাটস ওয়াই মাইনাস 1, দিস ইকুয়ালস টু 0। ইকুয়েশন 4 বোঝা গেছে? হ্যাঁ। Similarly, del summation ui hat square by del beta 2 hat is basically 2 summation yi minus beta 1 minus beta 2 hat x2i minus beta 3 x3i, and since beta 2 hat এর coefficients x2i ছিল with negative, that's why minus x2i must be equal to 0. Similarly, equation 6, del summation ui hat square by del beta 3 hat is equals to 0. Similarly, we are getting the equation 6. So now if we solve equation 4, 5 and 6, which is we can easily get the values. From equation 4, if we use equation 4 is summation 2 summation yi minus beta 1 hat minus beta 2 hat x2i minus beta 3 hat x3i equals to 0. Since 2 cannot be equals to 0 and minus 1 again cannot be equals to 0, that means the summation, this component must be equal to 0. This component has to be 0, right? That's why we have written, from equation 4, summation yi minus beta 1 hat minus beta 2 hat x2i minus beta 3 hat x3i equals 0. Now if we put summation in the bracket, that means summation yi minus beta 1 hat minus beta 2 hat summation x2i minus beta 3 hat x3i equals to 0. From where we are getting y bar equals to beta 1 hat minus beta 2 hat, এখানে একটা বার বসবে, হ্যাঁ এখানে একটু ভুল হয়েছে, x2 বার হওয়া উচিত, and minus beta 3 hat x3 বার। কেন বুঝতেই পারছো, বিকজ যখন তুমি সামেশন দিয়ে n দিয়ে ডিভাইড করবে ইকুয়েশন 4 কে, সামেশন করে n দিয়ে ডিভাইড করবে, তার মানে সামেশন yi বাই n মানে y বার। এবার বিটা 1 hat যেহেতু কনস্ট্যান্ট টার্ম, সেটা হয়ে যাবে n ইনটু বিটা 1 hat, n ইনটু বিটা 1 কে যদি n দিয়ে ডিভাইড করি তাহলেই বিটা 1 পাবো। সিমিলারলি বিটা 2 hat summation x2i by n means x2 bar minus beta 3 hat summation x3i by n means x3 bar। এটা তো লিখতে একটু অসুবিধা হয়, মানে এটা এডিট করার হয়নি, it should be x2 bar and x3 bar, clear? Okay, very good. So obviously, if we get the values of beta 2 and beta 3, we can easily get the values of beta 1 hat, because x2 bar and x3 bar is known to me from the given sample. Now from equation 5, we can easily write summation yi minus beta 1 hat minus beta 2 x2i minus beta 3 x3i times x2i has to be equals to 0. If we again do the same thing, we can easily get summation yi x2i minus beta 1 hat summation x2i minus beta 3 hat summation x2i square minus beta 3 hat summation x2i x3i. That means we can write this as summation yi x2i, and keeping all the left hand side values excluding summation yi x2i to the right hand side, we can get summation yi x2i equals to beta 1 hat summation x2i plus beta 2 hat summation x2i square plus beta 3 hat summation x2i x3i equals to 0. Similarly, from equation 6, we can write summation yi x3i in the right hand side and other things in the left hand side. So minus becomes plus, beta 1 hat summation x3i plus beta 2 hat summation x2i x3i plus beta 3 hat summation x3i square. Okay. So from 7 we can see that এখানে লিখেছি, ওখানে লিখতে ভুলে গেছিলাম, the beta 1 hat equals to y bar minus beta 2 hat x2 bar minus beta 3 hat x3 bar. Okay. Now এবার এইটাকে derivation is not so important in CU, অতটাও আসে না, এই জায়গাটা মেইনলি আসে না, কিন্তু এটাকে আমি এখানে সলভও করিনি, আমি জাস্ট লিখেছি। এটাকে আমরা অবভিয়াসলি দরকার লাগে পরে আমি ডিরাইভ করে দেখাতে পারি, আমি এটা দেখাইনি এখানে, জাস্ট আমি কোএফিসিয়েন্টটা কি হবে সেটা লিখেছি। সো বেসিক্যালি বিটা 2 হ্যাটটা আমার রেজাল্ট, আমি যদি এটাকে ডিরাইভ করি মানে কিছু না, জাস্ট বিটা 1 যেটা পেলাম সেটা যদি আমি এখানে পুট করে দিই বিটা 1 হ্যাটের জায়গায়, তাহলে সবটাই আমি x2y x বিটা 2 আর বিটা 3 টার্মসে পাবো ইকুয়েশন 8 আর 9, তাই না? ইকুয়েশন 8 আর 9 কে আমরা পাবো। তাহলে ইকুয়েশন আর 8 আর 9 কে যদি আমি ক্র্যামারস রুল অ্যাপ্লাই করি ও মার্টিনস রুল অ্যাপ্লাই, ক্র্যামারস রুল যদি অ্যাপ্লাই করি এখান থেকে আমি অবভিয়াসলি বিটা 1 আর বিটা 2 হ্যাট পেয়ে যাব। ঠিক আছে, সেটা যদি তোমার দরকার লাগে আমি খাতায় করে দেখাতে পারি। So following the convention of letting the lowercase letters denote deviation from sample mean values, one can derive the following formula from the normal equation 7, 8, 9. So obviously using 7, 8, 9 we can get beta 2 hat একটা important, beta 2 hat এর রেজাল্ট আমরা কি পাচ্ছি, summation yi x2i times summation x3i square minus summation yi x3i times summation x2i x3i whole divided by summation x2i square times summation x3i square minus summation x2i times x3i. Note that it is very important, in the previously we are assuming capital X. দেখো প্রথমে আমরা সবগুলোই capital X দিয়ে লিখছিলাম, but here we are writing it in a smaller form, that means it is a deviation from. Deviation from means we are writing everything in deviation from, mean deviation from, right? মানে সবগুলো observations কে আমি mean দিয়ে বাদ দিয়ে এইটা পাচ্ছি। So from this we can easily get the values of beta 2 hat and beta 3 hat, not necessary to derive those things, because we can easily get the beta 2 and beta 3 using any kind of like R regression, R shekho, we can easily get the values of beta 2 and beta 3 hat. No need to derive this. So this gives the Welles estimation of the population regression coefficients. Now in passing note, the equation 4, 5, 6 can also be written as equation 4 টা আমরা যদি আরেকবার ভালো করে দেখি, equation 4 টা is nothing but summation of ui hat, তাই না? তাহলে এখান থেকে আমি বলতেই পারি যে u bar equal summation ui hat equals to 0. Similarly equation 5 কে আমি বলতে পারি summation ui hat x2i equals to 0 and summation ui hat x3i equals to 0. These three are known as normal equations. In the two variable regression model we have two normal equations. In three variable regression models we have three. In three variable regression models we have more than we have three normal equations, which shows the properties of least square fit, namely that the residual sum of equals to 0 and they are uncorrelated with the explanatory variables x2 and x3, just like the assumptions. Now if we calculate the variance, we can easily calculate the variance by deriving that. Having obtained the Welles estimators of the partial regression coefficients, we can derive the variance and standard error of these estimators in the manner as indicated in the two variable case. The relevant formula are as follows. Variance of beta 1 hat এর রেজাল্ট আমরা এরকম পাই, এটা মনে রাখতেও as such হবে না, জাস্ট দেখে রাখো পরীক্ষায়। ভেরিয়েন্স অফ বিটা 2 হ্যাটটা একটু আলাদা মনে রাখতে হয়, বিকজ এখান থেকে আমাদের অনেক জিনিসপত্র বের হয়। ভেরিয়েন্স অফ বিটা 1 হ্যাটটা এটা। নেক্সট, ভেরিয়েন্স অফ বিটা 2 হ্যাট ইকুয়ালস টু সামেশন x3i স্কয়ার ডিভাইডেড বাই summation x2i square times summation x3i square minus summation x2i x3i whole square times sigma square, equation 14. Or equivalently we can write variance of beta 2 hat as sigma square by summation x2i square times 1 minus r square 2 3. খুব ইজি। আমি বেসিক্যালি এইখানটাতে আমরা যদি পুরোটাকে ডিরাইভ করি আমরা এটাই পাবো। আচ্ছা, ঠিক আছে। তাহলে এখানে দেখো r square 2 3 টা ইম্পর্টেন্ট। r square 2 3 মানে বেসিক্যালি কি, মানে কোরিলেশন বিটুইন, এক্স্যাক্টলি কোরিলেশন বিটুইন ভেরিয়েবল 2 and 3, তাই না? তাহলে কোরিলেশন বিটুইন ভেরিয়েবল 2 and 3 is r square 2 3, which is basically দেখাচ্ছে। So r square 2 3 is the sample coefficient of correlation between x2 and x3. Similarly, we can get variance of beta 3 hat as this, which can also be written as sigma square by summation x3i square times 1 minus r square 2 3, where r square 2 3 is the sample correlation coefficient between the variable 2 and 3, x2 and x3. From this, we can easily calculate the values of covariance of beta 2 and beta 3, which is minus of r square 2 3 times sigma square whole divided by 1 minus r square 2 3 times root over of small x2i square small x3i, root over of small x3i square. In all this formula, sigma square is the variance of the population disturbance term ui. Following the same argument as in the previous unit, we can easily verify that an unbiased estimator of sigma square, ওখানে কি ছিল simple linear regression model-এ sigma square was RSS by n minus 2. So here, because there are two variables and we need to estimate three parameters, beta 1 and beta 2 beta 3, that means we have n minus 3 degrees of freedom. So RSS by n minus 3 is the unbiased estimator of sigma square. Clear? Note the similarity between these estimators of sigma square and its two variable counterpart. The degrees of freedom are now n minus 3 because in estimating summation ui hat square, we must first estimate beta 1, beta 2 and beta 3, which consumes 3 degrees of freedom. The estimated sigma hat square can be computed from equation 19 once the residuals are available, but it can also be computed more readily by using the following relation. এটা আমরা আগেও দেখে এসেছি, মনে করে দেখো যে total sum of square TSS equals to ESS plus RSS, তাই তো? So basically this part is RSS, sorry, only this part is RSS, this part is TSS, total sum of square, and this part is explained sum of square, ESS, right? That means ESS plus RSS is equals to TSS. এটা আমরা আগেও করে এসেছিলাম, এখানে আরেকবার দেখছি। আমরা জানি যে ui hat is equals to yi minus beta 1 hat minus beta 2 hat x2y minus beta 3 hat x3y, which can also be written in the deviation form. No, মনে করে দেখো যখনই আমরা deviation ফর্মে লিখতাম beta 1 hat আর থাকে না, right? In the deviation form beta 1 hat cancels out, that's why ui hat equals to small yi minus beta 2 hat small x2y minus beta 3 small x3y, where small letters as usual indicates deviations from mean values. Now summation ui hat square can also be written as summation of ui hat into ui hat, right? Now we can easily write, in case instead of ui hat we can easily write yi minus beta 2 hat x2y minus beta 3 hat x3y from the previous equation. That means that we can easily write this as ui hat times yi, right? Now similarly we can write, keeping yi same, that the previous term ui hat as again yi minus beta 2 hat x2y minus beta 3y. Now if we multiply this, we are getting summation yi square minus beta 2 hat summation yi x2y minus beta 3 hat summation yi x3i, which is the required result. That means Here also we are getting that the total sum of square is sum of exponent sum of square and residual sum of square, where this term is total sum of square and these two terms are exponent sum of square. Now the properties of OLS estimator is very easy. The properties of OLS estimator. The properties of the OLS estimator of multiple linear regression model parallel those to the two variable model specifically are, আমরা আগেও এটা পড়েছিলাম মনে করে দেখো, in case of two variable model that y bar and x bar must pass through the or must pass যেখানটা intersect করছে that must pass through beta 1 and beta 2. Similarly, in case of three variable regression line surface, এটাকে আমি surface বলবো, why? Because this is a three dimensional space, right? Passes to the means of y bar, x2 bar and x3 bar, which is evident from equation 7. In the previously, in the two variable case, we have assumed that the two variable regression lines must pass through the mean values. তো এখানেও সেটা হোল্ড করা উচিত। Similarly, আমরা আগেও এটা পড়ে এসেছিলাম যে mean of yi hat is equals to mean of y bar. Here also we have the same property. The mean value of the estimated yi is equals to mean value of the actual yi, which is easy to prove. এটাও কিন্তু পরীক্ষায় আসতে পারে। We know that yi hat from the sample regression function yi hat equals to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i. Now we are writing here y bar minus beta 2 hat x2 bar minus beta 3 x3 bar. This is nothing but we are just putting y bar minus beta 2 hat x2 bar minus beta 3 x3 bar in place of beta 1 hat. We know that beta 1 hat is basically y bar minus beta 2 hat x2 bar minus beta 3 hat x3 bar from equation 4, right? Now keeping y bar as constant, y bar plus if we take beta 2 common, you will get x2i minus x2 bar. Similarly, if you take beta 3 common, you are getting x3i minus x3 bar. Here also x3 bar is not given. So these are basically in deviation from, that means yi hat is equals to y bar plus beta 2 hat x2i plus beta 3 hat x3i. Now if we sum both the sides over the sample values and if we divide throughout by n, that means summing both sides over the sample values and dividing throughout by the sample size n, what we are getting is that 1 by n summation yi hat equals to 1 by n summation y bar plus beta 2 hat times 1 by n summation x2i plus beta 3 hat 1 by n summation x3i. And we know that in statistics we have studied that the sum of deviation from their mean is always equals to 0. Sum of deviation from their mean values is always equals to 0. আমরা পড়ে এসেছিলাম যে summation of xi minus x bar is equals to 0, right? প্রতিটা ভ্যালুকে যদি তার corresponding mean দিয়ে মাইনাস করে তাকে যদি অ্যাড করি, that leads to 0 result. That's why the other two terms in the right hand side, the second term and third term in the right hand side will be equivalent to 0. So what we are getting is that the yi hat bar is equals to y bar, which proves the notice that by virtue of this equation we can write yi hat minus y hat bar is equals to beta 2 hat x2i minus beta 3 hat x3i, right? We can easily write this. That means that yi hat, small yi hat is equals to beta 2 hat x2i plus beta 3 hat small x3i. Therefore the SRF can be expressed in the derivation form as equals to yi hat plus ui hat equals to 1 minute beta 2 hat x2i plus beta 3 hat x3i plus ui hat. Okay. Third property is, we know that the summation of ui hat is equals to u hat bar equals to 0. That means the mean of the residual term is equals to 0, which is obvious from equation 23 that if we write summation of yi, that from here we are easily getting summation ui hat to be 0. Next property similar to the simple regression function is that the ui hat is obviously uncorrelated to x2i and x3, which is obviously true from the two normal equations that we have studied above. That is summation ui hat x2i equals to 0 and summation ui hat x3i equals to 0, which means that ui hat is uncorrelated with x2i and x3i. Similarly, we can also prove that the residual term is also uncorrelated with yi hat. That is summation of ui hat yi hat equals to 0. How we are getting is that from equation 22. Let's see equation 22. This is my equation 22. Okay. If I multiply both sides of equation 22 by ui hat and then if we sum it, that means summation of ui hat yi hat equals to summation of beta 2 hat ui hat x2i plus summation beta 3 hat ui hat x3i. We know that from the two normal equations, summation of ui hat x2i equals to 0 and summation ui hat x3i equals to 0. And since beta 1 hat, beta 2 hat and beta 3 hat, beta 2 hat and beta 3 are constant terms, it will come before summation. That means beta 2 hat summation ui x2i equals to 0 and beta 3 hat summation ui hat x3i equals to 0. So from equation 15 and 17, it is clear that again from equations, if we see equation 15 and 17, this is my equation 15, which is variance of beta 2 hat equals to this, right? Sigma square by summation x2i minus 1 minus r square 2 3. Okay. Here, if sigma square rises, since sigma square is in the right hand is in the numerator of the right hand side, if sigma square rises, then variance will rise, right? Again, if summation x2i square rise, then also variance will fall down, right? Can you denominator? And if the correlation between the variable 2 and 3 rises, then also the variance will rise. And we know that increase in variance is not good, right? That's why the property 6 is from equation 15 and 17, it is clear that as the coefficient of correlation between variable 2 and variable 3, the correlation coefficient between x2 and x3 increases towards 1, the variance of beta 2 hat and beta 3 hat increases, right? Joto correlation বাড়বে x2 and x3 এর মধ্যে অত beta 2 and beta 3 hat এর যে variance টা বাড়বে for given values of summation x2i square, summation x3i square and sigma square. It is also clear that for given values of r2, 3, r correlation coefficient between 2 and 3, summation x2i square and summation x3i square, the variance of the OLS estimator are directly proportional to sigma square. That means sigma square joto বাড়বে, auto obviously variances in beta 1 hat and beta 2 hat will rise, right? Similarly, for the given values of sigma square and r square 2, 3, the variance of beta 2 hat is inversely proportional to, এটা কিন্তু properties দিলে পরীক্ষায় লিখতে হবে, variance of beta 2 hat is inversely proportional to summation small x2i square. That means the greater the variation in the sample values of x2, the smaller the variance and therefore beta 3 can estimate more precisely. যদি তোমার ভেরিয়েবলের মধ্যে হোমোজেনিটি বেশি থাকে তাহলে তুমি বিটা 2 এরটাকে ভালো করে এস্টিমেট করতে পারবে না। যদি x2 ভেরিয়েবলের মধ্যে বেশি হেটেরোজেনিটি থাকে among the sample, তার মানে তুমি অনেকগুলো জিনিস তোমার কাজে আনতে পারছো, অনেক ইনফরমেশনস বেশি কালেক্ট করতে পারছো, তাতে তুমি বিটা 2 এরটাকে বেশি আরো বেটার এস্টিমেট করতে পারবে। That's why the greater the variance in the sample values of x2, the smaller the variance and therefore beta 2 can estimate more precisely. Clear? Now, similar to the previous part, যেখানে আমরা মনে করে দেখো r square বের করেছিলাম, এখানেও আমরা multiple coefficient of denomination বের করতে পারি। In the two variable case, we saw that r square, that is goodness of fit, measures the goodness of fit of the regression equation. That is, goodness of fit কি দেখায় না it gives the proportion or percentage of total variation in the dependent variable y explained by the single explanatory variable x. This means that কতটা better তুমি regress করতে পারছো. It gives the proportion or percentage of total variation in the dependent variable y explained by the single explanatory variable x. This notion can be easily extended to regression model containing more than two variables. Thus, in the three variable model, we would like to know the proportion of the variation in y explained by the variables x2 and x3 jointly. The quantity that gives this information is known as multiple coefficient of determination and is denoted by r square. We know that from the probability regression function population regression function PRF, yi equals to beta 1 hat plus beta 2 hat x2y plus beta 3 hat x3y plus ui hat, which means that yi equals to yi hat plus ui hat. Now if we use the derivation form, we can write yi equals to beta 2 hat x2y plus beta 3 hat x3y plus ui hat. Again here beta 1 hat cancels out. That means yi equals to small yi hat plus ui hat. If we sum over it, and use square, that means using the formula of a plus b whole square, we can write a square plus b square plus 2ab in the form of summation yi square equals to summation yi hat square plus summation ui hat square plus 2 summation yi hat ui hat. And we know that from the property that the residual term and the yi hat are uncorrelated, so we can write summation yi hat ui hat to be 0, so we can write summation yi square is equal to summation yi hat square plus summation ui hat square. So obviously summation yi square is nothing but total sum of square, summation of yi hat square is nothing but excellent sum of square, and summation ui hat square is nothing but residual sum of square. Right? Now from equation 20 we can write summation of ui hat equals to, we know that this is basically summation ui hat equals to summation yi square minus beta 2 hat summation yi x3i minus beta 3 hat summation yi x3i. If we put this equation, we are getting this as summation of yi square plus summation yi square, sorry, it should be ui hat square minus beta 2 summation yi x2i minus beta 3 x3i, which on rearranging we are getting the explained sum of square as beta 2 hat plus summation equals, we know that ESS is this, again we know that r square is nothing but ESS by TSS, so r square is ESS by TSS means here it would be beta 2 hat summation yi x2y plus beta 3 hat summation yi x3i whole divided by summation yi square. Note that here r square lies between 0 and 1. We know if it is 1, the fitted regression line explains 100% of the variation in y. On the other hand, if it is 0, the model does not explain any variation in y. Typically, however, we know that r square lies between these two extreme values 0 and 1. The fit of the model is said to be better and the closer is r square to 1. Here we have other terms as adjusted r square, adjusted r bar square as well, that we will discuss in the later class. Okay, আমি adjusted r bar square টা পড়াবো যখন আমরা মাল্টিকুলারিটি পড়বো। আচ্ছা, ঠিক আছে।